Modern educational software doesn't run in a safe vacuum. It operates in a hostile cryptographic environment where standard web practices fail to protect student privacy. AlgoQuest is designed to solve this. It is a platform that collects incredibly granular data about how a student learns algorithms, but it presents two entirely different, isolated realities, one to the student and one to the teacher. This top left panel of the student dashboard embeds specific security flags directly into the learning path. The interface clearly marks that raw secrets are blocked and actively highlights privacy and secret risk flags during an assignment. The center planning console on the teacher's dashboard does the exact opposite. It enforces a strict redaction policy, hiding specific details and only showing an aggregate classroom need. This difference is a strict zero-trust cryptographic boundary, engineered directly into the application's architecture. To integrate AI safely into schools, policy promises fall short. Applications have to physically enforce these asymmetric data boundaries at the code level. The standard industry pipeline for educational apps is highly vulnerable. Peripheral learning tools typically stream raw, real-time student actions straight to a central cloud server, creating massive liability. AlgoQuest replaces this with a localized hub model, using its visual algorithm designer as the starting point for student tasks. This flowchart maps a data packet, a high-scoring student artifact, as it moves through the system. Before it ever leaves the app, it hits a hard architectural firewall and is actively scrubbed of all secret data tags. After the scrub, the packet does not go to the cloud. It is written directly to the browser's local storage queue, specifically matching this outbox schema. AlgoQuest then reads this localized queue, double-checking the payload against strict schemas and running secondary secret detection before allowing any further action. Because this validation happens entirely in the browser, the student's machine never needs to hold raw environment files or live API keys. Keeping the event queue locked inside local storage means massive cloud-level data breaches of intermediate student learning states are structurally impossible. The cloud never holds the data to begin with. This validated algorithm card on the student's surface shows exactly how the interface handles this localized data. It updates with specific details, tracking the number of attempts, and prompting the open challenge call to action, all driven by local memory. Running underneath the surface is an internal watchdog called the Qubit Companion Service. This helper acts as a bouncer. It is programmed to aggressively reject incoming payloads containing raw tokens, tracking cookies, or attempts to route through unapproved local model endpoints. Instead of relying on those vulnerable methods, the application forces all traffic through a highly regulated school routing protocol. The system relies on a secure WebAuth pipeline and a fingerprinted gateway approval sequence. This verifies the session and authenticates the student without exposing credentials to the broader network. The result is a student interface that provides high-fidelity, real-time feedback to the learner, while mathematically preventing credential leakage from the browser. Switching back to the teacher's dashboard, you might wonder why educators are deliberately blinded to the raw event queues we just examined. This planning console replaces raw student names and individual errors with masked, generalized data. It groups the information, showing an aggregation of 3 or more learners and a generalized tool recommendation count. This data flattening is driven by a specific architectural contract called the Education Metrics Envelope. It takes a cluster of individual student struggles, strips away the identifying markers, and translates them into a single redacted intervention recommendation, like extending a high score artifact for the group. Teachers are empowered to intervene at the classroom level, but they never hold the toxic liability of raw, individualized student behavioral records. This same architectural rigor applies to web accessibility, a critical requirement for EdTech that often creates a massive, unrecognized privacy loophole. The industry standard is to drop in third-party SaaS accessibility widgets. As this microscopic view illustrates, these tools often act like parasites, aggressively scraping telemetry and tracking user behavior across the screen. AlgoQuest completely bypasses this with a self-hosted edge user console, keeping the solution entirely privacy-first. Specific neurodivergent profiles, like a dyslexia support or an ADHD Sprint mode, are executed entirely through local CSS overrides rather than external cloud requests. Every single comfort setting and display preference is saved purely in the browser's local storage. True accessibility in educational technology must be computed at the edge. If an accessibility tool tracks a neurodivergent minor, it is structurally unsafe. This architectural map shows the AlgoQuest ecosystem operating across 3 isolated nodes: the Access Console, WebAuth pipeline, and locked local storage boundary. The ecosystem blocks unauthorized AI interference. Generic models and uncensored endpoints are rejected, leaving a glowing pathway to approved providers. Privacy and safety cannot be bolted onto educational software post-launch as an afterthought. Safety requires enforcing asymmetric data contracts from day one, isolating state within local storage, and pulling accessibility entirely to the edge. AI in the classroom is viable, but only when constrained by rigorous front-end governance that prioritizes student privacy above raw data aggregation.